Hello everyone, it's me, Professor Aaron Albert, here again with Lesson 30. Let's learn some econ. So, welcome to Block 3. We've made it most of the way. And for all of our fun, Block 3 begins with something a little different. Today we're going to start talking about game theory, and that doesn't require you to solve any Lagrange functions, which should be a refreshing change of pace. So today we're going to start by defining a game, quote unquote. We're talking about dominant strategies, dominated strategies, best responses, and Nash equilibrium. And first, we're going to talk about the assumptions behind game theory. We're going to show you how to solve for the pure strategy Nash equilibrium using best response functions. And next time, we'll talk about how to solve for mixed strategy equilibriums of static games. All right, so the first thing we should do is orientate ourselves to what a game is. Now, this might not look like a game to you, but to an economist, that's a game. So, in a basic static game, player 1, which is by convention said to be the player who chooses row, i.e. player 1 will either choose up or down, and player 2 will choose left or right. And, by convention, the payoffs are listed as player 1, player 2. So in this game, if player 1 chooses up and player 2 chooses left, player 1 will get 1 util and player 2 will get 2 utils. Conversely, if player 1 chooses down and player 2 chooses right, player 1 will get 1 util and player 2 will get 2 utils. And now, the things that make this interesting is, you'll note that the payoffs for each player depend upon the actions of the other player, right? If player 1 plays up, player 2 really likes to play left. However, if player 1 plays down, player 2 really doesn't want to play left, right? There's some sort of interaction. We cannot solve these as individual agents just thinking about themselves, like we did when we were talking about the consumer problem or the producer's problem. We'll begin these games by assuming that the two players choose among their option sets simultaneously, i.e. at the same time. We also assume that players are just looking at the bigger payoff number. And now this isn't much of an assumption, right? You might say, oh, well, player 1 really also likes it if player 2 gets bad values. That's fine. All you need to do is rewrite the box such that player 1 is rewarded for player 2 having lower values, right? All we care about is the numbers observed. Everything, including people's happiness from playing the game itself, is taken into account when we look at the actual payoffs for the game at hand. And as said, the reason games are interesting and different is because the best thing for each player to do depends upon the actions of the other player. And now I'm throwing around words like action. We should talk about what the actual definitions of all the different important words are. So first, there are important vocabulary words action and strategy. They are very similar, but the distinction is quite important. An action refers to a choice that a player can or did make, i.e. player 1's available actions are up or down. That means when the game is done, we could observe that player 1 has played up or down. That is the actions available to player 1. Similarly, player 2's actions available are left or right. Now, a strategy is some sort of marching orders. It's what the player is saying that they are going to do when they play this game. In a simple game like this, you'll note the actions and the strategies look very similar. For instance, for player 1, his actions are up or down. The choices regarding how he will play this game is, he could say, I am going to play up, or I'm going to play down. And the reason it's important to note that action and strategy are different is because they don't have to be the same thing. They're only going to be similar in cases where we have two players playing a game a single time and only playing it once and not randomizing. For instance, next class we'll talk about strategies where people mix, right? It could be that player 1's actions are up or down, and that his strategy is I'm going to flip a coin and then play either up or down based on the coin flip, i.e. play up or down 50% of the time. So, action, remember, the different options a person has at a particular moment in time. And strategy refers to the full battle plan, the marching orders, exactly what the person is going to do when they play this game. All right, now that we know what actions and strategies are, we should talk about how to solve these games. So the easiest way to solve these games, won't work every time, but sometimes it does, is to look for dominant strategies. In order to find dominant strategies, we should also talk about dominated strategies. So here I'm just going to read the bullets and put emphasis on the important words. Dominated strategy. That is a strategy that produces strictly lower payoffs than some other strategy for every possible rival strategy. That is converse to a dominant strategy. That is a strategy that produces strictly higher payoffs than some other strategy, no matter what the other player does. And the reason we need to talk about both dominant and dominated strategies is because we always want to play dominant strategies and we never want to play dominated strategies. And it seems redundant to talk about dominated and dominant strategies, right? If one strategy is dominant, that means the other strategy is dominated. This sort of complete opposition only exists in 2x2 games, right? We could have a game where player one has 3 strategies. One of those strategies is dominant, one of those strategies is dominated, and the third one's neither dominant or dominated. So we're just looking at 2x2 boxes for a minute, and you'll note that if they have a dominated, they have a dominant, but they could have some mixture of these two, or none of the above, or something. So first, practice break. Look at the payoffs in the game that I've drawn below, and tell me, does player 1 have a dominant strategy? Does player 1 have a dominated strategy? Does player 2 have a dominant strategy? Does player 2 have a dominant strategy? Let me know what you think of. All right, so looking at the definition, player 1 has a dominant strategy if they have a strategy that produces strictly higher payoffs no matter what the other person does. You'll note that up is strictly better than down if player 2 plays left, and up is strictly dominates player down if player 2 plays right. So it looks like up is a dominant strategy for player 1. Similarly, it looks like 0 is strictly worse than 1, 0 is strictly worse than 1. Therefore, player 1 has a dominated strategy, D. So I'm going to put a frowny face. This is dominated, and this is dominant. How about player 2? Well, for player 2, you'll note 2 is greater than 0, and 0 are the same. Let's look at the definitions. What do we do in this case? Well, you'll note it says strictly higher, strictly lower. In this case, player 2 doesn't have a dominant or dominated strategy. Why? Well, because if player 1 plays down, it doesn't matter what player 2 does. So neither strategy is strictly better or worse. The reason these are useful is it becomes clear what's going to happen in this game. Player 1, we know, should always play up no matter what. So this game simplifies. Player 1 plays up. And note, we're going to assume that player 2 is pretty bright. Player 2 knows that player 1's going to play up. Therefore, does it matter what player 2 does? Yes, they should choose left because 2 is greater than 0. That is how we'll solve games that have a dominant strategy. With that in mind, here is beginning examples for easy games. Determine in each if player 1 has a dominant strategy, and then determine if player 2 has a dominant strategy. And let me know how you do. All right, let's look at the first one. I see that 1 is strictly better than 0, and 0 is the same as 0, so no dominance here. I'm just going to put a squiggle. For left versus right, 1 is greater than 0, but 0 is the same as 0. So that looks like in box 1, neither player has a dominant or dominated strategy. Move to box 2. In box 2, up is better than down for player 1 if player 2 plays right. However, left, if player 2 plays left, player 1 wants to play down. So that one doesn't work. Conversely, 1 is better than 0 if player 1 plays up, if we're looking at player 2's payoffs. And 1's better than 0 if player 2 plays down, that means player 1 plays down, that means player 2 wants to play right. Therefore, again, there's no dominant strategies in the second one. Let's move to number 3. You'll note that if the player 1 plays up, they either get 2 instead of 0 or 3 instead of 2. That looks to me like up is a dominant strategy and down is a dominated strategy. Looking for player 2, 2 is greater than 0 and 3 is greater than 2. That means left appears to be a dominant strategy and right appears to be a dominated strategy. Whew. Last one. If we look for player 1, 2 beats 1, 6 beats 4. That means dominant, dominated. Similarly, 2 beats 1, 6 beats 4. That means dominant and dominated. Hopefully you have those all right. Moving on. So, the way we'll solve all of these static games is to look for what's called a best response function. A best response is a strategy that maximizes a player's payoff given their beliefs about a rival's strategies. That is, if player 1 plays up, player 2 knows they should play left, right? If player 1 is believed to be playing up, player 2 then looks at their 0 and their 2 and says they should play left. The best response for player 2 to player 1 playing up is for player 2 to play left. Similarly, the best response for player 2 if player 1 plays down is to play left or right. Doesn't matter. And now the reason we want Nash equilibrium, the reason we want best response is it tells us how to find a Nash equilibrium. The Nash equilibrium is a set of strategies in which all players are playing their best response functions. And the reason this is useful is because if they're both playing their best response, then there's no incentive to deviate. So, let's talk about how to find best responses. We find best responses very simply by doing the following. Go through the box and underline the best response for each player in each situation. That is, assume player 1 plays up, underline the best option for player 2. Assume player 1 plays down, underline the best option for player 2. And then do the same for the other player. Tell me, after you've done this, if you found what the solution should be to this game. Alrighty, let's assume player 2 plays left. If player 2 plays left, player 1 should play up. So I'm going to underline this. If player 2 plays right, player 1 should also play up. Player 2. If player 1 plays up, they like 2 more than 0, so they underline the 2. And if player 2 plays right, if player 1 plays down, player 2 doesn't care. You'll note only one cell has 2 underlines. That means that this is the Nash equilibrium. In this cell, both players are playing their best response. You'll note that this means there's no incentive for either player to deviate. So let's check. If we're here, does player 1 unilaterally want to deviate down? Well, 0 is worse than 1, so they're not going to go down. Next, does player 2 want to deviate right? Well, 0 is worse than 2, so they're not going to deviate right. That means this is a stable outcome. Therefore, we believe that this is a quote-unquote Nash equilibrium. All right, so let's do another one. In this one, we're trying to model a duopoly. We'll do more strategic firm behavior in a bit, but first let's look at just a silly 2x2 game. In this, United Airlines is the column player, and they can either pick 64 or 48 flights per day. American Airlines is the row player. They can also either choose 65 or 48 flights per day. You'll note the millions of dollars in profit the two companies make changes based on how many flights they each make. First question, does either party have a dominant strategy? If so, we'll just focus on that. Look at the payoffs. Tell me what you think. Well, it looks like playing up is strictly better than playing down. it also looks like playing left is strictly better than playing right. Therefore, if we know that they're going to play up and left, that's the solution. To prove that that's the solution, i.e. that's the Nash equilibrium, let's check for deviation. Player 1 doesn't want to go down. Player 2 doesn't want to go right. That's the game. You'll note that this is a funny example. In fact, it is a classic game theory example because we think the Nash equilibrium is 4-1-4-1. However, is that the good solution? I would say no. Right, we could introduce the concept of Pareto optimal. You'll remember that from before. And you'd note that 4-1-4-1 is not a Pareto optimal solution. That is, 4-6-4-6 is in the bottom right-hand corner. And that is better for both players. So it's very hard for society to justify 4-1-4-1 as a good outcome. That is, they are incentivized to play up and left. However, if they could find some way to cooperate, they'd both get more. And it's very unfortunate because if they're at up left, the column player can only unilaterally move to the top right, and they won't do that. And the row player can only unilaterally move to the bottom left, and they don't want to do that. Right? There's no way for them to move to the bottom right because they can only control the actions of themselves. Worse yet, imagine by some accident they ended up on the bottom right. They just ended up at 4-6-4-6. Well, that's not even stable. If they ever ended up here by accident, player 1 would deviate upwards, and or player 2 would deviate leftwards. So there's no hope for them to ever arrive at 4-6-4-6 in this game. And these are the kinds of situations game theory is good at trying to illustrate. Sometimes what is incentivized for us is not necessarily what is good. You will note that they have a dominant strategy, as we said, up and left, and therefore they are incentivized to play up and left. All right, so now we're getting fancy here. Here is a 3x3 version of the same game. Go through and determine if there's any dominant strategy. Also go through and determine if there's any dominated strategy. And then go through and determine what the best responses are for each player, and see if you can tell me what the Nash equilibrium is. All right, let's see how you did. So let's assume that player 2 plays left. If that's the case, then player 1 will want to play down. Player 2 plays middle, player 1 wants to play middle. Player 2 plays right, player 1 wants to play, looks like middle. Reversing the process, player 1 plays up, player 2 plays right. Player 1 plays center, player 2 plays center. Player 1 plays down, player 2 plays, looks like center. Therefore, do we have any boxes with a double underline? Looks to be a yes. Looks like they'll arrive at 4-1-4-1. Now, could we have eliminated any strategies off the bat? Well, if you look, player 1 should never play up. Up is strictly dominated by playing center, right? Playing center is better in every single case, strictly speaking. So by getting the game, we can just delete up. It is never going to be played. How about for player 2? If we've deleted up, player 2 might notice that playing left is strictly worse than playing middle. 3-1 worse than 4-1, 4-6 worse than 5-1. So we can also just delete left. And then we're stuck with this 2x2 game. If we look at this 2x2 game, we could also try to see again if there's any dominant strategies. Again, it looks like center from this reduced game dominates down. We can delete that. Then we're left with just these two. We could delete right. And therefore, we'd conclude that through the deletion of dominated strategies in sequential pattern like that, we'd still arrive at 4-1-4-1. Two ways to solve the same game. All right, here's one more. Look at this game. Tell me if there's any dominant strategies. And then, if there's not, use the underlining method and tell me if you can find the Nash equilibrium. Alrighty, let's look. Looks like 1 beats 0, but -1 is worse, so player 1 does not have a dominant strategy. Looks like 1 beats 0, but -1 is worse, so player 2 does not have a dominated strategy. Okay, moving on to underlines. Player 1 would play enter if player 2 does not. And conversely, if they do. Reversing, player 1 plays up means player 2 plays right. Player 1 plays down, player 2 plays left. That tells me that we have 2 Nash equilibrium. To check, let's see if there's incentive or deviation. Player 1 does not want to go up, player 2 does not want to go right. So this looks to work. Similarly, player 1 does not want to go down, player 2 doesn't want to go left. So it looks like this one works. This is done to illustrate the point that sometimes multiple Nash equilibriums is completely possible. In fact, in a 2x2 game, it's possible to have 0, 1, 2, 3, or 4 Nash equilibriums, all completely possible. All right, that brings us to last goal of the day. Go through and tell me what the Nash equilibrium is in each box. And after that, I'll see how you did. Go. All right, let's check the first game. 1 beats 0, 1 beats 0. And, let's see, 1 beats 0. And then actually, I can underline both of these because it doesn't matter. 1 beats 0, and then it doesn't matter this way. So it looks like game 1 has 2 Nash equilibriums. The bottom right is slightly surprising since it's a 0-0, but you'll note that due to the ties, there's no incentive to deviate. Let's try this one. Player 1 would play down, up. Player 2 would play left, right. Looks like there's no Nash equilibriums. Moving to 3. Looks like player 1 would play up here, up here. Player 2 would play left here, left here. Looks like our Nash equilibrium's on the top left. Moving to the last one, looks like player 1 plays up here, up here. Player 2 plays left here, left here. Again, looks like our Nash equilibrium's in the top left. That's all that we have time for today. Thanks so much. See you next time.